rest until you see something. Here we go, and just make sure it's close to you. Yeah. Okay. Oh, also, I got some feedback about too few breaks. So I've scheduled for one break in the morning and one in the afternoon. In the afternoon we'll have coffee and sweets. The lunch is a bit later today. It's 1:30. The same down in the hotel. And also, some of you had problems hearing the questions, so I'm thinking that maybe if you think it's a good idea, we could pass around the microphone when we have Q&A sessions between the presentations. So I'll try to remember to pass it around and let me know if you need it. All right, great. Take it away.
Okay. Lua and a residential gateway. So, first, who am I? Software engineer for over 10 years in Technicolor. So I've seen a few things. My office where I work is based in Edegem, Belgium. That's a few kilometers south of Antwerp. Technicolor, maybe you know us, but then you probably know us from the movies. Well, that's a big chunk of what the company does. So movie, special effects, post-processing, Blu-ray, DVD, manufacturing and distribution, everything related to movies and animation and special effects, that kind of stuff. So that's like 45% of the company's revenue. MP3 patent, also very famous. It's largely owned by Technicolor, source of income, together with lots of patents in MPEG. That's also us. But we also have a big division that manufactures gateways, set-top boxes, so DSL gateways, cable gateways. And in fact, we're actually #1 in the world. If you look at numbers of units, revenue, but you don't find us in the shops because we manufacture and deliver directly to the service providers. And most of the time they are not showing our logo, but the logo of the manufacturer. And in fact, for the Swedish guys here, Telia is one of our customers, so you might think a few other people here might actually have one of our gateways in their homes, which is running Lua. In numbers, I looked it up. This year we shipped our 200 millionth set-top box. So we're talking about that kind of numbers. A little bit of history in our connected home division and where it's coming from, and then more specifically the DSL gateways, because that's where I'm working on. In the 90s you had Alcatel with a big office in Antwerp, and they were working on DSLAMs. And they also started developing modems, because if you're developing a DSLAM, you will also need another device to connect to the DSLAM and to test everything. So they also started working on CPEs, on modems, at that time. And then around 2001, they sold the modem business because they wanted to focus on the back-end side. And they sold it to what was then called Thomson Multimedia. And then they rebranded themselves under the one Technicolor brand because it's of course more known than this Thomson Multimedia. So that's where we are coming from. A lot of the people that I work with actually originated in Alcatel and then they moved to Thomson. If you look at the device, the gateway itself, at first it was a rather simple device, a modem bridge. If you had one of these, you might remember you had to install a PPP client on your Windows that would connect to the internet. So it's a rather simple device, but of course that meant you had only one PC that you could connect to the internet. unless you started finicking with maybe an early Linux. So that was not that very user-friendly, and so the thing started evolving. So ATM, PPP, protocol support got built into the device. You added a switch, you started to implement routing, added support for protocols like DHCP, DNS, you had to add a firewall, of course, and also, unfortunately, NAT. Then you had the big explosion in wireless standards, ABG, NAC, all had to be added to that device. Voice over IP, another big software blob and hardware. Speeds got faster and faster, more and more functionality. Quality of service comes into play, services like DLNA all got jammed into that little box. If you look at the architecture of the thing, in the beginning, Alcatel started with doing it themselves. Own hardware, so they designed the PCBs. At a certain moment, they actually designed the chips themselves, but eventually they stopped doing that. The simple real-time operating system, you code it in assembler C. And of course, they implemented their own networking stack, their own protocols, and that's what was inherited by Thomson Multimedia, that group of people. And then they started building all these protocols on top of that, started implementing that, so the thing grew and grew. It evolved. In the end, like I said, they stopped making their own hardware. They started buying that from specialized vendors, system on a chip, so more and more stuff got integrated in the hardware. The operating system also started evolving. At a certain moment we had a architecture where the chip had a dual core, and on one core there was running a real-time operating system, running basically the networking stack. And on the other core you had a Linux that was more running the applications, the management applications. That was still our own drivers and our own networking stack. Of course, if you look at the technologies that had to be added, it kept growing and growing and growing. So at a certain moment that does not become maintainable with an in-house development team unless you start growing immensely, but that's not commercially feasible anymore. Programming this thing was mostly C, but we started introducing a little bit of Lua at that moment, mainly for the web UI of the device. So at a certain moment in time, this was no longer sustainable, and we did a radical shift. So now what we're doing is we take the system on a chips from the vendors with their drivers. Right now they're Linux drivers, and we took the OpenWRT Linux base, so the distribution OpenWRT, and we started building on top of that to create basically a new software architecture for our current gateways. So still running C, but Lua is now a very big player in the software of this system. If you look at managing a gateway, so like I said, this gateway has become quite a complex beast. Not only to manage all those different functionalities, but even at a lower level, if you look at the hardware, the chips, okay, it's MIPS. Most of the time it's a MIPS chip, although we're now seeing the transition to ARM. But what the chip vendors also include there is a lot of other hardware accelerators in there. And all these things also need to be configured in the correct way. So the management of this gateway is becoming also quite complex. If you look at the kind of management channels that you have, Web UI, it's a big visible one, but also a remote management channel for the service provider, because the service provider wants to manage all these thousands and thousands of boxes that they have in the field. That's through a TR69 protocol. Of course, you have a CLI, so either over serial, which is mostly used by us, the developers, but also Telnet SSH, hopefully SSH, although we still have sometimes customers that want Telnet access. But this is also mostly for developers and for the service providers, for the technicians to debug or do some in the field adjustments if really needed. Most of the time for the end users, CLI is closed. You also have UPnP and a derivative TR64. SNMP is also still there. So lots of different management channels, and there's a problem with that because there's more or less an implicit assumption in all of these that they are the management channel. So getting them all to work together in a nice way is, well, sometimes a bit of a challenge. But managing a gateway is also more than that. If you look at it from an enterprise point of view, is you have to manage firmware upgrades. So you have these boxes in the field for a service provider. At a certain moment in time, they need to be upgraded. So you push a new binary to the device. And it has to happen fast, and it has to happen in a robust way. So how do you manage that? In that build, you have factory default settings for the service provider, but also the user can configure certain things themselves. So they have user settings saved on the device. If you do a firmware upgrade, you need to manage that. Backwards compatibility of these settings needs to be managed. Also, another aspect is production. We are shipping lots of these devices, so they have to be flashed with the correct binary for the firmware, with the correct factory defaults in there. That's all stuff that needs to be managed in a correct way. And then, of course, in all these areas, security is quite important. So a device and gateway is an entry point to your local network. All these things need to be secured. And then for us, there is another aspect that is quite a challenge, and that is a matter of scaling. Scaling the software and scaling all these gateways. Because like I said, we ship a lot of them. Right now, I think we have 1 or 2 dozen different flavors of platforms of DSL gateways, so different hardware platforms. So you have these basic routers which have just a switch, a wireless, and a DSL interface, nothing more. 11-end wireless. You have more high-end gateways which have the full-blown voice over IP stacks and DECT support, and 11 AC wireless and VDSL and an Ethernet 1 port and everything. USB or not USB, so all these kind of combinations, dozens of platforms that we need to support from the same code base, more or less. And also we have roughly about 100 or more customers that we are actually delivering gateways to. And each of them, of course, have their own requirements on the way they have their network set up, the way they want to show the web UI to a user, and so on and so on. So how do you manage that kind of scale in one software image, one software base? Because we deliver several images, of course. Well, it's clear that the development teams themselves, they cannot create fully customized builds for each of these customers. That's simply not possible to push that to development teams. So what we do to do this kind of scaling is we have we call a technical sales group. It's a whole bunch of people that are distributed over the world. They have contacts with a service provider in that area. They know them. And when a service provider comes to us or we see an opportunity, the technical sales go to these potential customers, and they take along a bunch of platforms, or one of them if it's clear what the provider wants, and it comes with a generic build developed by R&D. And they go to the service provider and they start talking and they start testing in their labs and they start customizing that build until it more or less does what that customer wants. And then they can finalize this build and we can go actually in production. That means that you need to have a good generic software core developed by the development teams. But at the same time, that core needs to be customizable, very customizable, but of course in a bit of a user-friendly way. Technical sales guys, they are technical. They have a good knowledge about all the different technologies, but they're not programmers. They're problem solvers. So what they need is a good system that is customizable. But for us, the developers, what we want to have a good core that we can protect a little bit and that we can give to the technical sales, but they should only be able to customize what we give them to be customized, and they shouldn't touch the core because then we can get into instabilities of the software, or although they are very inventive, those guys. So we deliver a generic build, so a binary. It's compiled, it's built on our build farm. It goes to a repository and those guys can take it and they can start customizing. That means customizing, if they want to customize something, they should be able to customize it in a way that does not require recompilation of software, because that's not possible. Because also builds are signed and bootloaders will only accept builds that are signed by the correct keys and so on. So what we have is a system where the real core is compiled and is available, but they cannot touch it. They can only customize certain files. And after that, the customized files are reintegrated in the root file system, and we have a customized build that they can actually deliver. So no recompilation possible. Now, if we look at the management plane of a typical OpenWRT system, configuration is stored in what they call UCI files. UCI is a plain, simple text format that contains the settings, factory defaults. And what daemons typically do, if it's a daemon that was written specifically for OpenWRT, like the NetIFD, which is their core daemon managing the connections, the interfaces, the network setup. Those daemons read these UCI config files for their settings, and then they can start and do their thing. If you have open source daemons, what they do is they publish, or you can configure it in a UCI file, and then the init script reads the UCI file and translates it to command line arguments, or they generate a configuration file in the specific format for that daemon. But most of the configuration is in a uniform UCI format. But that's configuration. There's also state information or RPCs. If you want to say, okay, bring down this interface, that's an RPC. So what they have is a UBus daemon, UBus microbus, because they said dbus is too big. We write our own microbus. So that's just a simple dbus-alike daemon. Another daemon can expose certain RPCs through that UBus daemon, and they can publish events through that UBus system to listeners that can listen for that. So that's roughly their management plane, and then they have their web UI that basically just reads UCI files. and can access UBus daemon for state information or for doing RPCs. Good thing is UCI and UBus have Lua bindings. They come out of the box for free in OpenWRT, which is a good thing. So that's a good starting point for us. The thing that is missing for us was, well, the remote management capabilities. You cannot sell a box that does not have remote management capabilities. It's crucial for the service providers. So a service provider wants to have a connection to all these boxes in the field and manage that from their backend. This is, like I said, there is a standardized TR69 protocol. It's developed inside the Broadband Forum, which is a committee or a standardization organization in the broadband world that develops all these kind of protocols for managing gateways. TR69 is the remote management protocol that they standardized on. What you have on that, on one hand you have the protocol, but the data model that you access through this protocol, it's also standardized. It looks something like that. So the IGD, Internet Gateway Device data model, this is only a small part of the list. There's also a Device 2 data model, which is a successor to IGD. So there's this huge list of object types and parameters described in that standard. And that's basically what you have to implement as a vendor if you want to have your gateway remote, to be able to have it remotely manageable. So you need to have a daemon, CWMP, it stands for CPE Wand Management Protocol. We have that, of course, from the past already. But of course, that daemon only implements the protocol part, the data model part. Yeah, you need to somehow implement that list of IGD stuff that I showed, and you have to implement that on top of what your platform provides. So how do you do that? Well, the fact that I'm here means we're using Lua for that. In the past, we had it implemented in C, which I can guarantee you is not fun to implement that kind of stuff. Because the logic that you have to implement there can be easy or it can be quite complex. And yeah, you don't want to write that kind of stuff in C. It's a big pain in the ass. You have memory leaks, null pointer accesses, buffer overflows, so no, that's not fun. And second, it's not customizable at all without recompilation. So no, what we did is when we switched to OpenWRT based software architecture, we said, well, let's do this properly and let's use Lua for this. What we came up with is something called Transformer. Okay, that's for the geeks among us. We got to play with Transformer again. That was fun. So what we wrote is this Transformer thing, and we said, well, our CWMP daemon talks to this Transformer daemon, more or less following TR69 semantics and protocol. And then how you map or how you implement these different object types described in the spec, you write a mapping file for that. So a mapping file is nothing more than a Lua file implementing one or more object types and how that maps to the system underneath. So just a core, we're using SQLite for some persistency. And you add mapping files, mapping implementations, and Transformer will load them and use them. Now for this mapping, mapping consists roughly of two parts. There's a part with metadata describing the object types and all the properties of that object type. And since that is pretty boring to write and error prone if you do it by hand, We wrote a generator for that because that's easy. Broadband Forum publishes this complete data model in an XML file, so we wrote a generator, reads the XML file and spits out for a certain object type a nice Lua description that forms the start of your mopping implementation. And then you only need to add logic functions to actually implement that on top of the UCI and UBus and so on, sources of information. The generator is, of course, a Lua script. How does this look in code? So the left part is a piece of metadata spit out by the generator. That's all kinds of attributes and information that transformer needs to implement it properly. We're not using all the attributes at this moment. We're not even generating all of the attributes at this moment because there are a lot of them. But they are there. And we can use it if we want to, if we extend the core to actually do something with that information. And at the right side, you see pieces of code that you add to make this object type definition, well, usable by the core. So you add, for instance, a get implementation, which is something that transformer core uses to get actual values for a certain parameter. Now, Lua gives us a lot of flexibility in how you can write such a implementation, such a mopping. This example shows that the get field is a table which has an entry for each of the parameters in the metadata description. The top one is a function, so that function in this case is accessing a proc file, reading that and putting it in the correct format, and that's how we implemented the uptime parameter. So it's just a function. If you might as well allow, if you have a parameter that has a fixed value, you just put the fixed value there, not a function, and the core will know what to do. It doesn't make sense to have just a function that always returns the same value. It's a bit overkill. The manufacturer one is a bit more complicated. So we actually are fetching stuff from UCI. But in this case, this is a parameter that is not really constant at build time, but it is constant at runtime. Because once a box of software is packaged and has a correct factory default, it never changes at runtime. So we have a function at the start. Whenever this parameter is requested for the first time, we go through all the logic. Once we have a value, we now override the parameter in the struct and we put just the value there instead of the function. So the next time the parameter is requested, the value is there, and there's no function to be called anymore. In fact, the function is garbage collected. Code is gone, memory is free. That's a nice feature. In fact, it can be even more flexible. A get does not necessarily have to be a table. You can just also give it a function. That function will be responsible for getting all the parameters. That's not a separate function for every parameter. So a lot of flexibility in how you write this kind of code. If I think back on the presentations yesterday on the gaming frameworks and their biggest nightmare, meaning garbage that can hinder your performance. If you look closely, you see this is also not very optimal code. For instance, here, if this function is called, it's generating a table, a temporary table that is almost immediately garbage. So yes, it's not optimal code, can be optimized, and yes, we see if you do a get of the complete system, you see that there's a lot of garbage being generated. Right now, it's not a problem yet. We had a look recently it is, yeah, we might have to do something in the future. So transformer is really pure Lua code. We have a few small bindings to C libraries. So there's UCI, UBus, we have a small socket library. And I quickly calculated roughly 5,500 actual lines of code for the core itself. So excluding mopping implementations and some helper code there. So it really is a daemon listening on a socket that on startup loads all mopping files in a certain directory and then just p calls them. If somebody wrote a stupid syntax error, we catch it, print a nice stack trace and continue. If there's no syntax error but they fail to implement a get function for a certain parameter, that's sanity checks that we do, then again the loading will generate an error, we catch it, print the stack trace, and we can continue. When a request comes in, we decode it, we process it, and we invoke all these mopping functions as needed, and code the response and send it back. Now the thing that we have to do is we have to do the streaming. You cannot, well, if somebody says give me the complete data model, that is a lot of data, and you cannot just aggregate it in Transformer until you have it all and send it back to the client. That's simply too much data, so you really need to do it streaming. As you are processing the request and are descending in the tree, you generate data and you send it off to the client. So of course you do that with coroutines. Makes it really simple to iterate in a tree structure and yield your data and continue where you left off. In fact, it looks very, very simple. So if you look at the core get implementation at the top, it really is simple. You have your store containing the structure of the data model. You say we navigate, we start navigating, starting from this path. It's a get operation. And navigate, well, it just returns a wrapped coroutine and an iteration state. And that thing yields objects, different objects in the data model. For each object you call params, and that will return you each parameter. And you return that data, and it gets stored in a response buffer. The buffer is full, we flush it to the client. Actually very simple code to write. Corresponding C code was a lot worse. I can guarantee. Error handling, also interesting. How do you deal with errors? So this has to be robust. This daemon, there's not much room for errors. It's very simple. At the top level, when a request comes in, the request handler, basically the piece of code I showed, that is p called. So whenever we start navigating and we encounter an error, like the user gave a path that does not exist, we simply throw an error, and it will propagate up. Anywhere where we are in our code, we just throw an error and propagates up. Simple. Also, when we invoke a mopping function, we p call it because you never know what a mopping function does. Catch the error, package it in the right way, and throw it up again, and so on. Just to be sure, we have a watchdog p call around the main function. If that should ever fail, we can actually restart the complete system. So, experience with writing this thing was, compared to the old legacy implementation in C, this was very, very fast to develop. So I think when we started with the OpenWRT architecture, which was basically starting from scratch, I think we started shipping a first product, a basic wireless DSL router, nothing fancy, in about a year and a half. Roughly a year and a half, maybe 2 years, with roughly 2 teams, so let's say 10, 20 engineers, that's it. And we built this system with only 2 guys more or less. So it's very fast to develop. And it's stable, it just works. So you write it, a little bit of testing, a few little bugs, refactor a little bit as you start implementing more, but all in all it's very stable. So the amount of bugs we get for the core itself, that was very little, so good for us. And most importantly, Moppings have the flexibility they need to implement their functionality, and also most of all the Moppings are Lua code, so that means it's text. It can be customized easily because vendors want to add their own vendor extension parameters to the data model and so on. So all in all, very good experience. Another thing where we are using Lua for is, well, of course, the web UI. Web UI is what the end user sees, and of course the service provider, they have very strong opinions on how this should look like, which for us means it has to be very customizable, and technical sales guys need to be able to tweak this web UI until the customer is satisfied. But also the web UI is the first channel of attack. So we have to make sure it's secure, and that basically means do not write it in C. That's asking for trouble. So of course we don't do that. What we use is Nginx and Nginx Lua. It's very why? Well, it's proven technology. I mean, if it's good enough for Cloudflare and so on, then it sure is good enough for us. Maybe it's a little bit overkill, this kind of daemon for our needs, but well, since it's proven and it's very flexible, well, what is the alternative? I think it was a quick decision to just say, well, let's use that. Also, the fact that it's single-threaded and the non-blocking design, that also fits quite nicely with Lua, because Lua itself is only supports single-threaded. In the past, we actually had a typical web server that was using threads, worker threads, to process requests. Well, we did a kind of a Lua module for that, but getting that to work in that multi-threaded environment was, well, a very big pain in the ass to make that work reliably. So this was nicely fitting. You just write your code and in a seemingly synchronous way, and it works nicely. And on top of that, we wrote a little web framework that handles things like authentication, authorization, session management. You have a little page rendering there based on Lua pages. It's actually not that complex, and it's good enough. It works. Security-wise, well, all data is retrieved via transformer again. We will be implementing things like access control on transformer, so that you only have access to certain parts of the data model. Helps a bit in security. If you look at things like CSRF protection, what the web framework does is we monkey patch the Nginx Lua API to get your post data. And what the web framework mandates is it says that, well, if you send a post in, make sure that the CSRF token is there. So the web framework maintains a token in the session, make sure it is in the page, and make sure it is sent back in the post, because if you, in your page, request the post arguments, we will make sure that we check for the token presence, and if it's not there, the request is completely rejected. That means that a guy who writes a page does not have to worry about this thing. It's already taken care of. Technical sales guys are not developers. They don't really know all the ins and outs of writing a secure page. So that means that they don't have to worry. We monkey patch this thing and it works. The other main attack factor on a web UI is, of course, cross-site scripting vulnerabilities. There we have an interesting, I hope, approach. Is what we do is strings coming from untrusted sources, and untrusted sources are basically request parameters, but also data that is coming through transformer, because from the web framework point of view that is untrusted. We attach a kind of a taint to these strings. And what we then also do is we monkey patch, for instance, a string functions to propagate this taint. So if you do a G-sub or a match or whatever, the results coming out will propagate the taint properly. And then when you actually output your string using nginx.print or something, you will check for the presence of the taint. If it's there, we do a kind of a last resort HTML escape before we actually send it out. It's not 100% secure, but this actually closes a lot of the possible attacks related to XSS without a page author to actually worry about it. Because technical sales guys, you cannot rely on them to always properly escape their values before sending it to the client. That simply does not work. Now, how do you implement this taint? New proxy. You wrap a string in a user data, in a simple user data, and attach a whole bunch of meta methods to make it seem that this user data is still a string. That works quite okay, but since we're using Lua 5.1, that means that there are a few cases where that doesn't work. Simple example, if you have such a tainted string and you compare it with a string literal, what happens? Well, it's always false because the two are of a different type. And that in Lua 5.1, it's by definition, it's always false. So unfortunately, we had to patch the VM to make that work in the way we want to make it work. It wasn't actually that difficult, which I found quite nice. You can patch the internals of the VM to make this work. Okay. Some other uses. One sensing. So if you have a customer like Telia, for instance, they support VDSL connections, but also Ethernet 1 connections. And what they of course want to do is have one device that they deliver to the customer, and the customer arrives at his home and he just plugs in either a DSL cable or Ethernet 1 cable, and the device should simply work. So what we have is you put the base configuration in the software, and then you have a one sensing state machine basically that will kick in when VDSL syncs or when your Ethernet comes up, and it will sense which connection scenario is expected, and it will complete the config and actually bring up the one connection. Written in Lua, just a daemon. It's basically a state machine, and you can customize the different states and what happens in the states. So again, for the technical sales guys, they arrive at a potential customer, they just tweak this kind of thing and show that it works. Another thing, LEDs. You cannot imagine how important LEDs are. Again, service providers have very strict requirements on how the LEDs should behave, but yeah, they are different from each customer. So if you have one wants to have a blinking red LED if something is wrong, and the other one wants a solid red LED, so it again has to be very customizable, and again we implement that in Lua in a customizable state machine. And a third use, host manager, a Lua daemon that discovers the hosts connected to the gateway, collects some info on which port is it connected, which is the speed of that connection, and so on. And information is published via UBus, and of course then we can use it in the web UI, for instance. Tooling wise, we are using internally, most of the guys use Eclipse with the Lua development tools. It's there and it works. But there's another quite interesting reason why we're using Eclipse, and that's the Remote System Explorer plugin of Eclipse. So that's a nice plugin that can use, for instance, SSH to connect to a target, and then it can show you the file system. You can browse a file system of the remote target as if it's local, and if you double click on a file, it will transparently transfer it to your local machine in a temporary file and open it in your editor. You start editing it, you do save, and it will transfer it back to the target. So it looks like transparently editing on a target, you're just like you're working directly onto the target. And of course that means this is a huge productivity boost for us. If you as a developer can develop your transformer or your one sensing thing, and you can directly edit it on target, make a change, restart the thing, see if it works, if it doesn't work, and so on. That's a huge productivity boost compared to classical writing it in C, recompiling, transfer the thing back onto the gateway. That's an enormous productivity boost, and it's one of the main reasons why we were so fast in developing a new software based on this architecture. Small tools, LUnit, Lomoc, LuaCheck, LDoc, typical ones. Lomoc is also, I think, a nice example of flexibility of Lua. If you want to test something, you probably want to mock certain parts of the system so you can actually reach certain code paths, error paths typically. You want to test this fully. Yeah, with monkey patching again, you can actually insert the mocks and trigger the behavior that you want. Very, very useful. Compared to C again, this is an order of magnitude easier to write if you compare it to CMOC, for instance. And of course, when you write tests, you also want to know what is my code coverage. Those were homegrown at the time when we started with this. I didn't really find good tools that were meeting our needs. And if you think a little bit about it, how hard can it be to write this? Let's try this. And actually, indeed, it wasn't that hard to write. So now we run tests under a little code coverage model. So it's just a module, you load it, you run your tests, and it will generate all kinds of information. Well, when you run the test, it will just output each line that is being hit. You just insert a debug hook, and that data is then processed offline, and it generates a nice HTML report. So for each file generates a coverage score, and when you click on the link, it actually shows you a nice syntax highlighted view of the sources, and it will on the left say how many times a line was hit, and if a line was never hit, even highlights it in bright red. So you know you have to write another test maybe. A similar thing, we have a small profiling module, also not bad, a dozen lines of code maybe. And you just do it like that, start profiling at a certain point, and insert these points where you want to have a timing, and that will output a nicely indented call graph with timings. We also in the past had an implementation where we just used a debug hook again, so that you would do this automatically for each function call. But that works for a small piece of code, but so if you run it on something like Transformer, it generates a huge amount of data. That does not really work. But the thing is, what I like about this is that you can actually write this kind of tools in the language itself. That's, I think, a very nice property of the language if you can do that kind of thing. Something that is missing in this view, a debugger. Yeah, I've never actually really felt the need for a debugger, strangely enough. Just by reasoning about what is going on, you have a stack trace, or you enable a bit more logs, you can quickly figure out what's going on and fix it. So there's not really a need for a debugger. Okay, so to conclude, future for us, well, simple, use more Lua. It just works and it helps us to do more work in a shorter amount of time. I'm interested to have a closer look at Lua 5.3. So like I said, we're still on 5.1 because that's what OpenWRT had from the beginning. But since OpenWRT and the hardware that we are using is MIPS without floating point unit, so OpenWRT integrated the famous LNUM patch to have this dual number support. And it's quite a bit of a intrusive patch, so it would be nice if we can use a Lua version that has this kind of functionality out of the box. Bitwise operator is also a good, nice thing. And from 5.2, light C functions, non-tagging has a promise of less memory usage, also something that we're interested in. To be experimenting with, and of course, Lua JIT. If I now hear about a MIPS port with soft float, maybe something to take a look at in the future. FFI also something interesting if we can use that instead of handwriting or bindings. Maybe it's useful. On the other hand, if we implement that kind of stuff, then the technical sales guys can actually access all C code in the system, so maybe that's not a good idea to do that. But in the end, we're actually pretty happy with what we have right now, and it works quite well. So there's no real need to upstep to 5.3, and maybe we will stick with 5.1 for quite a long time. We'll see. That's it. Open for questions.
So I have two questions actually. The first one is what's the lowest memory in the system? What is the lowest amount to run in this?
I think the lowest end platform that we currently selling, I think it's 64 megabyte of RAM.
The second one is also the web UI. You look at AUCI.
Yes. Yeah, we had a look at the beginning, but at that time we felt it was complex, not quite well documented either, and it seemed to lack the flexibility and the documentation that we needed to be able to support all our engineers. So if you then compare that to Nginx and Nginx Lua, that has a fantastic good documentation, which is also very useful for those guys.
What is conversation process with what?
Whether we looked at the standard OpenWRT web UI framework. And also, their framework is homegrown, so security-wise, performance-wise, also one of the factors.
Okay, you said that you have some libraries, like security libraries and some libraries and that kind of stuff on top of Nginx. Have you actually released anything on the public, or have you planned to do it?
No. Not really sure how useful it is, since it's of course quite tailored to our use cases. Also open sourcing something in a company like ours, it's a bit of an administrative nightmare sometimes. So no, there's no real plans to do that. Sorry.
No more questions?
Do you have to perform some kind of memory management or garbage?
Good question. Good question. Up until now, we don't do anything special. Recently, we had a bit of an investigation on what is happening, especially in Transformer, because it executes a lot of code and can generate quite some garbage. And when you look at how the system behaves, you see that indeed there is quite a kind of a peak going on if you do a big request, because there's a lot of garbage being generated, and if you then at the end of the request do a collect garbage, you see there's quite a drop. So yes, there's room for optimizations, but right now there's no real need yet. So unless there is really a problem, we have a few ideas on how we can mitigate this, but no real need yet. Okay, thank you.